So our main goal is going to be to try and translate D'Alembert's principle, which is written in terms of the 3n coordinates of the particles, into the generalized coordinates, which is a smaller set. And remember that the generalized coordinates are such that you can get coordinates for any particle just out of the generalized coordinates, and there are explicitly s of those. Okay, what that means is that the velocity, say, which is defined as just the rate of change of the position with respect to time, well, we just take a total derivative of this, because each of these coordinates might be changing with respect to time. So we have sum over k, which goes 1 to s, plus, of course, any explicit dependence. Okay, so Vj can be calculated very simply. So taking those derivatives is how we converted from movement in our generalized coordinates to movements in our original coordinates. And we also want to go from our displacements in our original coordinates to displacements in our generalized coordinates. And we do this in exactly the same way. And now we substitute the displacements in the original coordinates with the displacements in terms of the generalized coordinates, where all we've done is replaced this increment here with the increment where we derived over here. Now this first term here, we have the sum of the forces of each particle times this derivative here. That actually has a bit of a physical interpretation. You can see that this depends on k, qk, and qk, if we define that to be, then what this qk really is, it's the generalized force in the direction of the kth generalized coordinate. And we can come back over here and we can write, and this is not a dot product anymore, this is, we're summing over the s generalized coordinates that we have. And I'll put these other terms on the other side in a slightly strange way. And you can see that if I take the derivative of this, I will get the first term from my product rule will be exactly that. So I also have to take away the other term from my product rule, which is r dot times the time derivative of this. Now we have to do a little bit of extra algebra here in order to massage this, so try and stay on for the ride. You can always go back over it if you need to. The first extra tool we're going to need, we can get from up here. What we have is we have that Vj is sum over k, and if I interpret this, that's just q dot plus the explicit time dependence. So if I was to take the derivative of Vj with respect to qk dot, what would I get? I would get this term. So this implies, and of course this is exactly what we've got over here, so I'm going to replace that in. But first I want to look at one other result. Looking at this, this is the derivative, the time derivative of this derivative here. I've already done the time derivative of just r itself, and this is the same thing except I've already got one derivative on the r. But actually it'll come out the same way, because this is a function of all the q's. This is a function of all the q's. So I'm going to get, plus I'm going to have the explicit term, which we can see from up here is just equal to the derivative of v of I with respect to qk. So what we're going to do now is we're going to take this result here and put it up into that. We're going to take this result here and put it up into there and rewrite this equation. And what we've done here is we've got something extremely familiar. This is the kinetic energy of the ith particle. And you'll note that none of these things depend on I, so I can take this sum over I all the way into there, and I got the total kinetic energy. And that's a very important result. So we've now got the generalized forces all in terms of qk's, and we've got everything here just in terms of a scalar function and the qk. So if I can work out the kinetic energy in terms of my generalized coordinates, then I have an equation that's fully in terms of my generalized coordinates. We can actually go further, because these generalized forces here often come from a potential, and if they come from a potential, then we can expand this form as well. So if all of these applied forces come from some kind of external potential, then what we can say is that our qk's can be written as minus sum I, the gradient using the coordinates ri of the potential, dotted with this. And it might take a moment to spot, but if you stare at that for a little bit, or possibly if you work backwards, it's easy to convince yourself that this is exactly what you get if you take the derivative of the potential with respect to qk. because this v is actually a function of all of these variables, r1 vector, r2 vector, and so on. And each of these is comprised of 3, so we're going to get a sum over all the i's, and we're going to get a sum that's this dot product, and that's exactly what you get when you take the total derivative of this. And so that's just derivative of v with respect to qk. So when we come back over to our equation over here, we have, and if we put these both on the same side, and we note that this potential only depends on the coordinates and doesn't depend on q dot. So this term is derivative with respect to qk, so they just kind of add together, except we'll get a t minus a v. And this term, if we took a derivative with respect to q dot, we get 0, so we can put one in there as well. And so when we add all of that together, what we get is this. And now we use a very simple argument that says that these movements here could have been completely arbitrary, and this equation has to be true. So if this equation is true no matter what these things are, if they're completely arbitrary, then if this sum has to be 0, then in fact each of these terms individually has to be 0. And that is an extremely familiar looking equation. That looks exactly like the Euler-Lagrange equation. And if we make one final definition, the Lagrangian is simply equal to the kinetic energy minus the potential energy, then we write this as the Euler-Lagrange equation that shows us pretty clearly that this object called the Lagrangian, integrated over time, appears to be either maximized or minimized. And so that's the Euler-Lagrange equation for mechanics.